Welcome to today's lecture of the course Mathematical Aspects of Biomedical Electronic System Design. This is the last lecture on the module Probability and Random Variables. In today's lecture we will cover joint and marginal distributions, conditional distributions, independence of random variables, covariance and correlation. So let us start today's lecture. We will start with the notion of joint distribution. Suppose we have n random variables on the same space. X1 dot 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 xn on space omega f, then the function which is from Rn to 0 1, that is it takes n-dimensional real vectors and gives an output that is a number between 0 1 defined by f x1 dot 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 xn equal to probability of capital X1 less than small x1, capital X2 less than or equal to small x2 dot 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 capital Xn less than or equal to small xn. That is probability of the event, that is intersection of the events xi omega less than or equal to xi. This function is called the joint distribution of x1 to xn. It's called the joint distribution of x1 dot 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 xn. To proceed further, let us consider the case of discrete and continuous random variables separately. So, discrete random variables. So now we assume that the variables x1 to xn are all discrete. If x1 dot 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 xn are all discrete, then there exists a function p, and this function is again from Rn to 0 1 such that the joint distribution, that is fx1 dot 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 xn, is equal to y1 less than or equal to x1, y2 less than or equal to x2 dot 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 yn less than or equal to xn, p of y1 y2 dot 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 yn. This function p is called the joint probability mass function. The function p, which as we saw is from Rn to 0 1, is called the joint mass function of x1 to xn. Now consider continuous random variables. If x1 to xn are all continuous, then also there exists a function f from Rn to R plus this time, so this can take values larger than 1, such that the joint distribution fx1 x2 dot 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 xn can be expressed as minus infinity to x1 minus infinity to x2 dot 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 minus infinity to xn f of y1 y2 dot 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 yn dy1 dy2 dot 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 dyn, and this function small f is called the joint probability density function. The function f which is from Rn to R plus, this is called the joint probability density function of x1 to xn. Let us consider a simple example to illustrate a few of these concepts. Consider the following experiment. A coin is tossed twice, and let us define random variables x1 to be number of heads in the first flip, in the first toss. Clearly x1 can take value 0 or 1. x2 is number of heads in the second toss, and y1 is number of tails in the first toss. Okay, in this case we can consider pairs of random variables x1 x2 x1 y1 x2 y1 etc., and we can talk of their joint distributions. For instance, if we consider x1 and x2, the joint distribution of x1 x2, f x1 x2 can be obtained as follows. So f x1 x2 0 0, it will be probability that x1 is less than or equal to 0 and x2 is also less than or equal to 0. That is, there is no head in the first toss and no head in the second toss either, and clearly this is 1/4. fx1 x2 0 1, that is no head in the first toss and either 0 or 1 head in the second toss. So outcome of the second toss is immaterial, but there has to be tail in the first toss. So clearly this is half. Similarly, fx1 x2 1 0 will also be half. fx1 x2 1 1 is probability that there is 0 or 1 head in the first toss and 0 or 1 head in the second toss. Clearly this will be 1. Similarly, if we consider x1 y1, then joint distribution of x1 y1 can be obtained as follows. So f x1 y1 0 0, that is no head in the first toss and no tail also in the first toss. This is impossible event, so the probability of this event will be 0. If x1 y1 at 0 1 can be obtained as probability of no head in the first toss and 0 or 1 tail in the first toss. Clearly intersection of these two events will be event that there is no head in the first toss, and that probability will be half. Similarly, the joint distribution evaluated at 1 0 will also be half. The joint distribution evaluated at 1 1 will be probability that there is 0 or 1 head in the first toss and there is 0 or 1 tail in the first toss. Clearly the probability of this event will be 1. So this is how we can evaluate joint distributions. Okay. Next we will move to marginal distributions. Suppose we are given n random variables on the same space and their joint distribution is f. So given random variables x1 dot 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 xn on same probability space and their joint distribution is f, then the functions fi, these are functions from R to 0 1 defined by fi of xi equal to f infinity dot 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 xi dot 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 infinity. Here we have infinity at all positions but ith position. So this is ith position. Right? Everywhere else we have infinity. So this is how the functions fi are defined for all I equal to 1 to n. In fact, we can see that the right hand side equals probability of x1 being less than infinity dot 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 xi minus 1 being less than infinity, xi being less than or equal to small xi plus 1 being less than infinity, and dot 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 xn being less than infinity. These functions are called marginal distributions. Are called marginal distributions. So fi is marginal distribution of xi. We can again consider the cases of discrete and continuous random variables separately. So let us look at discrete random variables. Okay, so assume that x1 to xn are all discrete. And have joint probability mass function. We defined it above. P. Then the functions pi, and these are functions from r to 0 1 defined by pixi is summation over all y1 dot 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 yi minus 1 yi plus 1 dot 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 yn of p y1 dot 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 yi minus 1 xi yi plus 1 dot 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 yn. These functions are called the marginal probability mass functions. Are called the marginal probability mass functions. We can define marginal distributions also from marginal probability mass function. In fact, it turns out that fi xi equals yi less than or equal to xi pi yi. Okay. Let us now turn to the case of continuous random variables. Suppose x1 to xn are all continuous. So these are all continuous with joint probability density function f, then we can define functions fi from r to r plus defined by fi equal to integral over y1 dot 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 integral over yi minus 1 yi plus 1 dot 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 yn f of y1 dot 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 yi minus 1 xi yi plus 1 dot 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 yn dy1 dot 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 dy I minus 1 dy I plus 1 dot 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 dyn. These functions are called marginal probability density functions. Are called marginal probability density functions. In case of continuous random variables, we can obtain marginal distributions also from marginal probability density functions. For instance, it turns out that fi xi is minus infinity to xi fi yi dyi. The concept of marginal distributions as defined above for n random variables might look complex but can be easily motivated by considering the case of two random variables. So let us see the special case of n equals to 2 to better understand the idea of marginal distributions. So in this case, if x1, x2 are two random variables, with joint distribution capital F, then we can write the marginal distributions F1, capital F1 and capital F2 as follows. F1 of x1 will be f of x1 comma infinity, f2 of x2 will be f of infinity comma x2 if x1 and x2 are discrete and have joint probability mass function, joint PMF P, then we can obtain the marginal PMFs P1 and P2 as follows. So P1 x1 will be summation over y2 P of x1 y2. Similarly, P2 x2 will be summation over y1 P of y1 x2. In either case, we can compute the marginal distribution as summation of marginal probability mass functions. On the other hand, if x1 x2 are continuous, if x1 and x2 are continuous with joint probability density function f, then we can compute the marginal probability density functions f1 and f2 as follows. Marginal probability density functions f1 x1 is given by integral over y2 of f x1 y2 dy2. Similarly, f2 x2 will be given by integral over y1 of f y1 x2 dy1. Again, for both x1 and x2, their marginal distributions can be computed by integrating the marginal probability density functions as described above. So this was about marginal distributions. Next, let us see the notion of conditional distributions. Here we will restrict attention to two random variables. Given two random variables x and y on same space, say omega f, we define conditional distribution of x given y equals to small y, and this is defined only if the probability mass function of y evaluated at y is strictly positive. In case y is discrete, or the probability density function of y evaluated at small y is strictly positive in case y is continuous. In such cases, we can define the conditional distribution of x by fx given y, small x given small y, equal to probability that x less than or equal to small x given capital Y equal to small y. This is for all small x. Let us again consider the cases of discrete and continuous random variables separately. So first let us consider the case of discrete random variables. If x and y are discrete, then we can define conditional probability mass function of x given y is small y, and of course this is given that probability mass function of y at y is strictly positive, as px given y small x given small y equal to pxy xy, that is joint probability mass function divided by marginal probability mass function of y all x. Notice that the right hand side can also be written using Bayes rule as follows. It can be written as pxx py given x y given x divided by pyy. This is Bayes rule for discrete random variables. Random variables. From conditional probability mass function, we can compute the conditional distribution of x as follows. Conditional CDF of x given y, x given y can be computed as summation z less than or equal to small x, px given y, z given y. Further, we can define conditional expectation of x given y equals to small y, denoted as expected value of x given y equals to small y, to be the expectation with respect to the above conditional probability mass function. That is, this is sum over all x, x px given y, small x given small y. We can also define conditional variance of x given y equals to small y. This is denoted as variance of x given y equals to small y. This is variance of x with respect to the above conditional probability mass function. This is variance of x with respect to the above probability mass function. So this is expected value of x minus expected value of x given y equals to small y, the whole square. Conditional expectation of this quantity, condition on y equals to small y, and this turns out to be equal to x square p x given y minus summation over x p x y x given y whole square. Notice that the first quantity is conditional second moment or second order moment, whereas the second quantity here is square of conditional expectation. This is conditional expectation. Let us see an example. Suppose we have two random variables x and y, discrete random variables that have joint probability mass function pxy small x small y as follows. It is 0.5 if small x small y is 1 1, it is 0.1 if small x small y is 1 2, it is 0.1 if small x small y is 2 1, and it is 0.3 if small x small y is 2 2. From the joint probability mass function, we can compute the marginal probability mass function of y as follows. Y of 1 will be summation of pxy 1 1 plus pxy 2 1, and this turns out to be 0.6. Similarly, py2 will be 0.4. Having computed the marginal probability mass function, we can compute the conditional probability mass function of x given y. In particular, probability of x given y 1 given 1 can be computed as joint probability mass function divided by marginal, and this will be 0.5 by 0.6, that is 5 by 6. We could similarly compute px given y 0 given as pxy01 divided by py1, and this clearly is 0.1 divided by 0.6, that is 1 by 6. Next, we turn our attention to continuous random variables. If x and y are continuous, we define conditional probability density function of x given y equals to small y. Conditional probability density function of x given y equals to small y. Of course, it's defined only when density of y at small y is strictly positive. This is defined by fx given y small x given small y equal to joint probability density function fxy xy divided by the marginal probability density function of y. Again, using the Bayes rule, it can be seen that the right hand side expression here equals fxx fy given x given y divided by fyy. So here what we have used is density version of the Bayes rule. Having obtained the conditional probability density function, we can obtain the conditional distribution of x as follows. Conditional distribution, that is fx given y x given y equals integral of conditional probability density function, so minus infinity to x fx given y z given y dz. We can also define conditional expectation of x given y equals to small y. This is denoted as expected value of x given y equals to small y. This is expectation of x with respect to the conditional probability density function defined above. That is, it is minus infinity to infinity x f x y x given y dx. We can also define conditional variance of x given y equals to small y. This is denoted as variance of x given y equals to small y. This is variance of x with respect to the above conditional probability density function. So it is expectation of x minus expected value of x given y equals to small y whole square, given that y equals to small y, and this turns out to be equal to minus infinity to infinity x square fx given y x given y dx minus minus infinity to infinity x fx given y x given y dx whole square. As in discrete case, the first term is conditional second moment of x, conditional second order moment of x, and the second term is square of the conditional expectation. So this is conditional expectation. Let us illustrate few of these notions again with an example. For this example, let us consider two random variables x and y and a region S defined as follows. So this region we call S. These points are 0, 1 and 1. So xy pair takes values in this region. Okay. And the probability of xy pair taking any value in this region is same. So joint density function of x and y is a constant which is 2 for all xy in S. The region to pick 2 here is, we need to satisfy the following condition: fxy xy dx dy integrated over this whole region should be 1, and this region itself has area half, so we need to pick this to be equal to 2 to make this whole integral 1. So this is the joint probability density function of x and y. From joint probability density function we can compute the marginal density of y as follows. So we want to compute fyy. Notice that for fixed y, x can range from 0 to 1 minus y. So fyy, which will be integral of fxy xy dx from minus infinity to infinity, this turns out to be equal to 0 to 1 minus y 2 dx, which is twice of 1 minus y. This is for all y in 0, 1. Having defined the marginal probability density function of x, we can compute the conditional probability density function of x given y, that is fx given y, small x given small y, as ratio of joint probability density function divided by marginal probability density function of y. So this turns out to be equal to 2 divided by 2 1 minus y, which is 1 over 1 minus y. In this definition, we assume that y is less than 1, as when y is equal to 1, the marginal density of y at 1 is 0, so this conditional density is not defined. Having defined the conditional density of x, we now turn to conditional expectation of x given y equals to small y, and this is simply the expectation with respect to the above defined conditional density. So it will be x times 1 minus y dx, and so this turns out to be equal to 1 minus y by 2. We can also write conditional variance of x given y equals to small y. This will be 0 to 1 minus y x square divided by 1 minus y dx minus square of the conditional mean, so 1 minus y by 2 whole square, and this turns out to be equal to 1 minus y whole square by 3 minus 1 minus y whole square by 4, and so this is 1 minus y whole square by 12. Now we will see the notion of independence of random variables. Random variables x1 to xn defined on same space are called independent if their joint distribution equals the product of marginal distribution. That is, if f x1 dot 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 xn is product of marginals fi xi, and this must hold for all x1 dot 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 xn in R. If the random variables x1 to xn are discrete, then an equivalent definition of independence is that these random variables are independent if their joint probability mass function is product of marginal probability mass functions. That is, if p x1 dot 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 xn equals product of I equals to 1 to n pi xi for all x1 dot 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 xn in R. Similarly, if these random variables x1 to xn are continuous, then also we have an alternate definition of independence. That is, these random variables are independent if their joint density is product of marginal densities. This is product of fi xi, I equals to 1 to n, and this again must hold for all x1 dot 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 xn in R. Here is a property of independent random variables. If x1 dot 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 xn are independent, then expectation of their product, that is expectation of this product random variable, is product of expectations. I equals to 1 to n expectation of xi. Let's see an example to see that independence is required for such a condition to hold. Example, let x be a zero mean random variable that is expected value of x is 0. Suppose y is also a random variable on the same space and y is actually twice of x, then expected value of y will be twice of expected value of x, and this will also be 0. However, if we consider product of x and y and take its expectation, expected value of xy, this will be expected value of x into 2x, that is expected value of 2x square, 2 times expected value of x square. This is strictly positive. So this is not equal to expected value of x times expected value of y. This illustrates that independence of random variables is required for the above relation to hold. Let's see one more fact. If x and y are independent random variables, and f and g are functions such that f of x and g of y are also random variables, then f of x and g of y are also independent. Let's now see a couple of more examples that illustrate how the property of independence of random variables can be used to compute the probability mass function or probability density function of some of those random variables. Examples. As the first example, let us assume that x1 and x2 are two independent binomial random variables. x1 is binomial with parameter n1 and p, and x2 is binomial with parameters n2 and p. x1 and x2 are independent. Let y be x1 plus x2. We are interested in probability mass function of y. That is, we are interested in probability that y will be some number m. Notice that y equal to m is equivalent to x1 plus x2 equal to m, and this latter event is union of disjoint events k equals to 0 to m, x1 equals to k, x2 equals to m minus k. If any of these events happen, the above event would also happen. Then using law of total probability, we can write probability of y equals to m as summation of k equals to 0 to m times joint probability of x1 equals to k, x2 equals to m minus k. At this point, we can exploit the fact that x1 and x2 are independent to write the right hand side as k equals to 0 to m px1, x1 equals to k times px2, x2 equals to m minus k. Since both x1 and x2 are binomial random variables, the terms inside the summation become equal to n1 choose k, p raised to k, 1 minus p raised to n1 minus k times n2 choose m minus k times p raised to m minus k times 1 minus p raised to n2 minus m minus k. In writing this, I assume that m is smaller than both n1 and n2, but similar calculation can be made for other values of m also. If we do the calculations correctly, the right hand side turns out to be n1 plus n2, choose m, p raised to m, 1 minus p raised to n1 plus n2 minus m. So looking at the form of probability mass function of y, we can infer that y is also binomial random variable with parameters n1 plus n2 comma p. Okay, so sum of two independent binomial random variables is also a binomial random variable. Let us now take second example, and now we assume that x1 and x2 are independent Poisson random variables. So that is x1 is Poisson with parameter lambda 1 and x2 is Poisson with parameter lambda 2. x1 and x2 are independent, and as before we define y to be x1 plus x2, and we are interested in probability mass function of y, that is we are interested in probability of y being m for an integer m, and as in the binomial case I can write it as a summation k equals to 0 to m probability that x1 equals to k, x2 equals to m minus k. Again, exploiting the fact that x1 and x2 are independent, we can write this summation as k equals to 0 to p x1 k p x2 m minus k. And since x1 and x2 both are Poisson, we can further write the right hand side as e raised to minus lambda 1 raised to k divided by factorial k times e raised to minus lambda 2 raised to m minus k divided by factorial m minus k, and this summation turns out to be equal to e raised to minus lambda 1 plus lambda 2 lambda 1 plus lambda 2 raised to m divided by factorial m. Again, looking at the probability mass function of y, we can infer that y is also a Poisson random variable. Y is Poisson with parameter lambda 1 plus lambda 2. So we see that sum of two Poisson random variables, if they are independent, is also a Poisson random variable with the parameter of this new variable being sum of the parameters of the original variable. Now let us see the notion of covariance. Given two random variables x and y on same space, their covariance is defined as COV, this is the notation, COV x comma y equal to expectation of x minus expectation of x times y minus expectation of y. Notice that the product here depends on both x and y. So this is expectation with respect to joint distribution. This expectation is with respect to the joint distribution of x and y. This expression turns out to be equal to expected value of xy minus expected value of x comma expected value of y. The second expression is obtained using linearity of expectation. Linearity of expectations. As above, the first expectation here is taken using the joint distribution of x and y. Let's see a few properties of covariance. First property is if x, y, g are random variables, and alpha, beta are two numbers, then covariance of alpha x plus beta y and z is alpha times covariance of x and z plus beta times covariance of y and z. Further, covariance of x comma alpha y plus beta z can also be written as alpha times covariance of x y plus beta times covariance of x and z. Second property is covariance of a random variable x with itself equals its variance. Another property is if x and y are independent random variables, then their covariance is 0. Let's see a couple of examples to understand the notion of covariance. The first example illustrates that x and y need not be independent for their covariance to be 0. Suppose x is a random variable with expectation 0 and the third moment of x is also 0. Let y be x square, then certainly x and y are not independent. Now let us compute the covariance of x and y. From the formula above, it is expected value of xy minus expected value of x comma expected value of y. Notice that y is x square, so the first term becomes expected value of x cube. As far as second term goes, expected value of x is 0. Though expected value of y, which is expected value of x square, is not 0, the second term becomes 0. From the hypothesis, the first term is also 0. So, we see that covariance of x and y here is 0 even though they are not independent. We take one more example that also shows the same fact. Let x be a random variable that is uniformly distributed over 1, 2, 3, and let y be another random variable, and this y is independent of x. And this is uniformly distributed over minus 1, 1. Let us define a third random variable z. which is product of x and y. Now consider x and z. We will first show that x and z are not independent. Towards this, let us consider the joint distribution of x and z evaluated at 1, 1. So fxz 1, 1, this is from definition probability that x less than or equal to 1, comma z less than or equal to 1. This is equivalent to probability that x less than or equal to 1, xy less than or equal to 1, which in turn is equal to probability that x is less than or equal to 1. This is because when x is less than or equal to 1, that is x is 1, the value of y does not matter, xy will be less than or equal to 1, and this is 1 by 3. Clearly, the marginal distribution of x at 1, fx1, which is probability that x is less than or equal to 1, is 1 by 3. Now see the marginal distribution of z at 1, that is probability of z less than or equal to 1, which is probability of xy less than or equal to 1. This can be written as probability that x is less than or equal to 1 plus probability that x greater than 1 but y is equal to minus 1. Notice that in the second case also xy will be less than or equal to 1. The first term is 1 by 3. The second term, since x and y are independent, can be written as 2 by 3 probability of x greater than 1 times probability of y being minus 1. The latter term is half. 2 and 2 get cancelled, and this way we get fz1 to be 2 by 3. Notice that fxz11 is 1 by 3, which is not equal to fx1 times fz1. So x and z are not independent. But as we show below, covariance of x and z is 0. To see this, let us first observe what is expectation of x times z. This is expectation of x times xy, that is expectation of x square y. This is expectation of x square times expectation of y. Notice that expectation of y is 0, so this turns out to be 0. Expectation of x alone is 1 plus 2 plus 3 by 3, that is 2. Expectation of z alone will be expectation of xy, which will again be expectation of x times expectation of y. This being 0, expectation of z also is 0. Now we can see that covariance of x comma z, which is expectation of xz minus expectation of x times expectation of z is 0. This is because the first term is 0 and here the last term is also 0. So again we see that covariance of two random variables can be 0 even though they are not independent. Finally, let us see the notion of correlation of random variables. Correlation. Given two random variables x and y, on same probability space, their correlation is defined as rho of x comma y, and it is covariance of x comma y divided by square root of variance of x times variance of y. For any two random variables x and y, the absolute value of covariance turns out to be less than or equal to square root of product of their variances. This implies that correlation of the random variables x and y is always between -1 and +1. Further, the random variables x and y are said to be uncorrelated if their correlation is 0, which is same as saying that their covariance is 0, i.e. if covariance of x comma y is 0. This quantity rho of x comma y is also known as correlation coefficient, also referred to as correlation coefficient. Let's see a few more facts about correlation. If the two random variables x and y are independent, then they are also uncorrelated. We have already seen that in this case x and y have zero covariance, that means they have zero correlation, so they are also uncorrelated. But the converse is not true. That is, if the correlation between two random variables is 0, that doesn't mean that they will be independent. We have already seen examples where two random variables had 0 covariance, that means they were uncorrelated but they were not independent. Next fact is, if x and y are uncorrelated, then variance of their summation is simply sum of their variances. The next fact is generalization of this fact. It says that variance of sum of random variables I equals to 1, 2 and xi is sum of their variances plus twice of sum of pairwise variances, as in this expression. Sum over I comma j. I and j are different. They are numbers between 1 and n. And here let's sum and we have covariance of xi comma xj. So this is the expression of variance of sum of random variables. This is general expression. This doesn't need the random variables to be independent. Clearly, if the random variables are independent, in that case they are uncorrelated. The second summation here becomes 0 and variance of summation becomes sum of variances. So in fact, if x1, xn are pairwise uncorrelated, that is their pairwise correlations are 0, all the terms in the second summation above become 0. So variance of sum of these random variables becomes sum of variances. We end with discussing the notion of covariance matrices. Given random variables, x1 dot 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 xn on the same space, the matrix capital sigma, it's an n cross n real valued matrix with elements capital sigma ij equal to covariance of xi xj. That is, it's a matrix whose elements are covariances of pairs of random variables. This matrix is called covariance matrix of the random vector x, which is nothing but x1 dot 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 xn. Okay, let us see a few facts about covariance matrices. The first fact is covariance matrix sigma is symmetric positive semi-definite matrix. It's symmetric positive, semi-definite. Next, the inverse of covariance matrix. If the covariance matrix is invertible, that is if the inverse exists, this inverse is called the precision matrix of the random vector x. That is x equal to x1 dot 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 xn. Finally, the covariance matrix turns out to be expectation of xx transpose if x1 dot 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 xn are all geomean. Notice that here in writing this, x is column vector of the random variables x1 to xn. So x transpose is row vector x1 dot dot xn. This implies that xx transpose is a n cross n matrix, random matrix. And in the above fact, we are talking of expectation of this matrix. This brings us to the end of today's lecture. Thank you everyone.